Welcome to the Deep Dive, where we take a stack of information, dissect it, and pull out the most important nuggets of knowledge to get you well informed, fast.
Great to be here.
Today, we're going to dive into something that I've always found fascinating, and it's absolutely critical to aviation safety, yet it often goes unnoticed until it's desperately needed. Aircraft landing gear and braking systems. Okay, let's unpack this.
It's true. These systems truly are the unsung heroes of every single flight, aren't they?
Absolutely.
When we think of aviation, our minds often go straight to, powerful engines pushing aircraft through the sky. But bringing that massive machine back to a safe, controlled halt on the ground, that's where these systems really prove their worth.
Yeah, exactly.
They're not just about stopping an aircraft. They're fundamental to safe maneuvering during taxi, protecting the airframe from colossal stresses and, ensuring that a vehicle weighing hundreds of tons, moving at incredible speeds, can transition safely from flight to ground operations. And for anyone studying for their ATPL theory exams, understanding these foundational principles isn't just about ticking boxes. It's really about grasping the core physics and ingenious engineering that underpin modern aviation and, frankly, keep us safe.
Couldn't agree more. Our deep dive today is primarily sourced from an insightful text specifically focused on aircraft brakes and braking systems.
Solid source.
Yeah. This source is going to be our comprehensive guide as we dissect the complex mechanisms and crucial safety protocols that are absolutely vital to these operations.
And for you, our curious learner, our mission today is, to distill all this intricate information into crystal clear insights.
Right.
We're going to give you those key facts, those vital distinctions that not only crucial for your ATPL theory exams, helping you confidently answer questions about everything from, say, brake fade to anti-skid systems, but also for a truly holistic understanding of how aircraft operate safely on the ground.
And we'll try to tackle some specific questions that pop up in exams, right?
Exactly. We'll be addressing some specific questions that frequently appear, making sure this isn't just a dry recitation, but an engaging conversation that brings these vital systems to life.
Great. So let's kick things off by putting ourselves in the shoes of the engineers and pilots. How do you actually bring something the size of a building, moving at hundreds of miles per hour, to a complete safe stop on a relatively short strip of concrete? It sounds like a problem right out of a physics textbook, doesn't it?
It really does.
The core principle at its heart is pretty simple. It's all about converting kinetic energy, the immense energy of motion, into heat energy through friction. Simple physics.
Basic principle, yeah.
But here's the kicker, and this is where the real engineering challenge lies. The amount of heat generated in this process is absolutely staggering.
Staggering is the right word.
We're talking about enough heat to melt metal if not properly managed. It's been a persistent, enormous challenge for aircraft designers and scientists for decades. And as aircraft have gotten faster, heavier, and more efficient in the air, this thermal management problem has only intensified.
Indeed. What's fascinating here is how engineers continually innovate to solve these fundamental physics problems, always pushing against the limits of material science and design.
It's incredible.
The ideal solution, if you think about it purely from a braking perspective, it would be to simply build runways so incredibly long, we're talking 4 or 5 miles, maybe even more, that an aircraft could just roll to a stop without needing its brakes at all.
Like the space shuttle landing almost.
Kind of, yeah. But of course, the prohibitive cost of land, the sheer logistics of building and maintaining such massive strips, and the environmental impact, it'd make that a complete non-starter. It's simply impractical for every airport in the world.
Right. Just not feasible.
So engineers turn to partial solutions, which have helped significantly in reducing the burden on the wheel brakes. These include the advent of reverse pitch on propeller-driven aircraft, where the propeller blades literally reverse their angle to push air forward.
Ah, interesting.
And reverse thrust on jet engines, which redirects engine exhaust to slow the aircraft. These systems provide a lot of initial stopping power.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.